Alright, time for another DraftPhysics.com and DebatePhysics.com video presentation. So we sort of have a civil video by STEPHEN Brough, and so we'll respond to it. A little patronizing, waste the first, it's a 3.5 minute video. He's going to do some instructing in 3.5 minutes. I don't think so. But anyway, so it's back to the Professor Lewin thing. I mean, it's in the title. The title's so long that I didn't even see that part. So he's going to help Gary understand Walter Lewin's elastic collision experiment. There's nothing to understand. It's a free momentum experiment. I've already explained how free momentum is free energy. I can make a perpetual motion machine. More importantly, I can make a free energy machine. I've diagrammed how easy it would be. It doesn't make any sense. It can't happen in the real universe, and obviously the experiment is flawed. Now, I've explained how it's flawed. It's obviously not a twice as massive cart, and I'll detail that once again in this video. So, I mean, again, if you're not going to respond to any of the arguments made, there's really no point in you making arguments that I respond to if you're not going to respond to any of the counter arguments. So, generally speaking, I have no confidence in your results. Your measurements of velocities, nothing. Okay, I mean, you've done experiments where you get results that contradict each other and or else prove a new theory. Neither prove kinetic energy or momentum, in neither one. Alright, so you waste the beginning of this video, sorry, but it's a waste of time, patronizing me about Newton's cradle. This isn't about Newton's cradle. This isn't about masses that are the same mass and the same energy and how that's transferred. It's about different masses interacting with each other. This is a subject covered by Descartes 350 years ago. Newton revised his numbers a little bit. People talked about what happens when a light object hits a heavy object, when a heavy object hits a light object. And some of it's accurate and inaccurate because it's hard to separate rolling things, okay, from moving things. So they didn't have air carts, but they did have pendulums. They had different ways to do experiments, and it really matters which way you do them. Okay, so that's part of the lesson I think you need to, you need to understand angular momentum and how, wheels are a problem, especially big, heavy wheels. But I'll go into that further into this video. So, alright, so just for the sake of, being counter-patronizing, let's understand what we're arguing, okay? We're arguing two theories, alright? I argue there's no compatibility between them at all. They're completely different definitions of reality. These two things cannot equal the same thing. They're completely different descriptions of reality. This one's really simple. Okay, all you look for is mass and velocity, and it can come in two forms. It can be a little mass and a big velocity, big mass, little velocity. You just weigh the amount of ink, okay, and that's it. Okay, momentum is a simple answer, and it's a really good answer. Descartes, Galileo, and Newton all believed this was all you needed to know. Okay, the end. This piece of crap came along much later. First it was just this, and then they stuck the half in front of it. And this means that these two things really just can't function the same, except in the circumstance where you can just say, well, this has kinetic energy, x, and I've got the same mass and the same velocity, and this has kinetic energy, x. So it only conserves when you have exactly the same masses and the same velocities. As soon as I change the mass and the velocity, or I change the velocities, as soon as I change the mass or I change the velocities, I can't change the mass without changing the velocities, obviously. I can take two same mass objects and I can change their velocities. Okay, I can have two velocity. All right, and the implications are already been stated. Okay, you sincerely believe that a car going 30 miles an hour and a car going 60 miles an hour, you sincerely believe that this one has 4 times the energy. Now, I see no reason to believe that. I see no evidence of it. It doesn't show up in real life. I don't see anything to indicate this is true at all. I can give all the other examples that I've given, boulders and all the other stuff. So that's the contest. There's no, these two things are survivable. They can coexist. They can't coexist. They're different definitions of a quantity, energy, okay, weight, power, all of those things, all right, and they're not compatible. So let's not play games that we're talking about Newton's cradle. We're not talking about Newton's cradle. All right. All right. So there's a lot of subjects in here. So all right. The experiment he's trying to defend is an experiment that basically does a very strange thing, right? It starts off with 100 momentums. The experiment creates, and going in the same direction, 130. And then you could just put another 2 mass, and you could end up with 160 and 100. You just keep increasing the amount of momentum. So you have a system, a machine, a box, an experiment. Okay, you put in something, and what comes out is more than you put in. Okay, and you get stuff going the opposite direction. Now they think, well, I guess Stephen believes that somehow there's such a thing as a negative bullet. I can shoot a bullet out of a gun, and I can somehow shoot a bullet the other way, and I'll undo this one. I can't undo what I've shot into the universe. This is real momentum, real mo. Okay, I can't have little mo here, 100 mo here, and have 130 mo here, and somehow I'm going to subtract whatever direction something bounces off. So it's like thinking if light reflects off a surface, that somehow it did both things. It went into the surface and it reflected. There's momentum in both directions. You can't do it in both directions. All right, it don't happen that way. And you certainly can't subtract one from the other. Okay, it's real momentum. I've described how to take advantage of it, make a perpetual motion, make a free energy machine. He hasn't debunked or in any way pointed out how you can't make the free energy machine by just banging masses. Take a 2 mass, bang it into a 4 mass, bang the 4 mass into an 8 mass, bang the 8 mass into a 16 mass, and you've doubled or tripled or quadrupled your momentum. And you can just recycle it and do it all over again, just over and over again, create more and more momentum. So it doesn't work logically. It has no hope of being correct, and it doesn't conserve momentum. Obviously. In my opinion, obviously. So I could ask Stephen if he believes in the conservation of momentum, because he's done a ton of experiments, and many of them don't conserve the momentum. So, do you believe momentum must be conserved? Do you believe it when Professor Lewin says you can finagle 1/2 mv squared, but nature can't finagle momentum? Do you believe him when he says that? Do you think he's true or saying something accurate? All right. So it's enough of making the point. Okay, so this is the experiment. The experiment is you crash a 1 into a 2. Okay, you end up with 2/3 of the same velocity in this object, which kind of means quite obviously that we got way too much velocity, right? You can't have half the mass. Okay, so it's the MV problem, right? You have a small mass and let's say a velocity, and then you have a little, twice the size of the mass, but you still have a pretty big V. So there's too much ink. Okay, the momentum doesn't add up. All right. It doesn't matter that you have this going the other way. The reflection isn't somehow undoing. There's no such thing as negative energy or unenergy or anti-energy. So I say this experiment is garbage. Now, the thing I can prove why it's garbage in one way is that you can point out how the premise of the experiment is false. This doesn't happen. They don't hit a 1 mass into a 2 mass. And it can be demonstrated that's a fact. Okay, so I'll make that argument again in this video, and I'll expect, frankly, that there's really no point in me responding to your points if you're not going to respond to any of mine. It's one of my arguments, just as the perpetual motion machine is one of my arguments. You have to show how it doesn't work. again, you debunk the Mythbusters video and say the whole thing's got to be thrown out by one tiny flaw, and the flaw doesn't mean much because it's still, the experiment doesn't show kinetic energy working. So whether it's 4 times or 3 times, there's no evidence of that 3 times in the product. There's just twice the compression, not 3 times the compression. So a tiny defect, frankly, you're saying is a catastrophic defect. Well, I'll show you a defect in your video, and you tell me. And I've shown defects in your other videos. I mean, do I have to go back to the beginning? And, well, I'll illustrate a couple of them. I'll save that for later, though. We'll get to the point as quickly as I can. Okay, as Stephen often does, he's arguing that this is some sort of flawless experiment that demonstrates it has great truth value, blah, 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 blah. I'd argue, it falls way short. But anyway, so Stephen Brough, by the way. Okay, so here's 2.5 kilograms into 4 kilograms. So he's getting close to the 2-to-1 relationship, or 1-to-2 relationship. So he's a little shy of that. All right. Okay, I probably have this volume up too loud. Okay, that should do. All right, so he says 71% of the take-up speed. That is he's just measuring the speed going forward. So we're obviously still way above how much energy should be going into the second cart. Now, I would argue that what Stephen's not realizing, because of the design of his cart, he has a ton of momentum caught up in the wheels. So this velocity speed, this 51 number, doesn't represent the real momentum in the system, because he has a bunch of momentum in the angular velocity of the wheels. The angular motion of the wheels contains a great deal of momentum that isn't going to be seen in your velocity. So when wheels turn, they turn in all directions. So it doesn't equal any direction, right? But it's still momentum. If I have a spinning wheel and I don't hit anything with it, I just let it spin, you understand it's a bunch of stored energy. And if I hit it against this wall, it'll cause motion this way. If I hit it against that wall, it'll cause motion this way. If I hit it against the top, it'll cause motion that way. If I hit it against the bottom, it'll cause motion that way. All right. So it's real momentum. So part of the force is in the angular momentum of the wheels, which has to be considered. Anyway. But you're still got to move the other cart's wheels, so you could also say, well, it's got to be equal in some sense. But I'm going to argue that that's why he's getting these weird results. It's because his wheels don't turn that easy. They have a lot of mass, and they require a certain amount of energy to get rolling. And so they don't roll easy because it's a lot of mass. All right. So anyway, so these are the numbers: 51 and 36 for a 2.5 kilograms. So now he's going to remove a full half of kilogram. So he's going to go to 2. So he's removing 1/5 of the mass, pushing with presumably the same force. He's using his hand as a release mechanism, which is really dicey. But anyway. And so it's going to move with more velocity. So we have the expectation that the going in velocity would go up. And we also have the expectation that the pushing velocity would go down because the cart is lighter. The lighter you get, like if I throw a little super ball at this cart, it bounces off and the cart doesn't move at all. So the lighter I get, the less energy goes into the cart. So I've removed a full half kilogram. And just remember these numbers: 51, 36.
The changes are becoming more and more obvious, aren't they? So let's go to 2 kilograms now.
So I would say that the flaws in the numbers is now going to be completely obvious. Okay, that these numbers aren't accurate and they can't be trusted. So now he's got the 2 to 1 relationship. 2 kilograms to 4. 1 to 2. 1 mass hitting 2 mass. All right. Now, it should be pointed out, he doesn't get numbers that are the 1.4 theory. He gets 1.55 or something. So his numbers don't work out. But anyway, look at the second number. It's exactly the same number. So we're supposed to believe that a cart that weighs 1/5 less put exactly the same. 363. It's even to the thousands, the same exact number. Does that make any sense? It's a much lighter cart, which means it should reflect more energy. So more energy. So there it is, 56. It's a full 5, which is a 10%. So there's 10% more energy going this way and exactly the same energy going the other way. That's implausible, frankly. It's not sensible. It doesn't make any sense. It's a linear line. Okay, it should be a linear line. How much energy goes into the other cart should be a linear line. As you make the cart lighter, the amount of energy going into the other cart should decline, just like that. Okay, so the lighter you get, the less energy goes into the forward cart. And here you have a whole 1/2 kilogram removed, and you have exactly the same forward momentum. And you don't think that's a significant, bizarre outcome, that somebody should say, well, that's not right. Somewhere the measurement's got to be wrong. One of these measurements has to be wrong. You've got more momentum, total momentum. So what did you do wrong? Where's the flaw? And again, you've got more total momentum, and you've got it in this weird proportion where it's exactly the opposite of the expectation. Less energy has to be going forward if more energy is going backward. So it doesn't make any sense. Not at all, right? 56 goes in. It's more energy going, it's more velocity going in. So we know we didn't lose much energy, okay? Yes, he's doing it by hand, so maybe he messed up and not as much went through. But 56 is 10% more velocity, so that's not bad. How can that possibly, on a lighter cart, produce the same outcome? Doesn't make any sense. All right. So yeah, it's enough said. So how is this a defense? And this just goes back to all of your experiments on this subject. All of them come up with erroneous results. So maybe all right, I should do the angular momentum thing first. Just to point out that it's significant. It's got to be, it's not a non-relevant detail. It does make a difference. So all of these frickin' experiments have flaws. The air track doesn't have wheels, so there's no problem with angular momentum. That's a good thing. But the carts can do this, which means they can be lifted up at one end and actually exhaust air and be propelled, which is a bad thing. But the whole idea is, if you have a cart, what you want to do, okay, is ideally have all the motion in the object moving. And you want to have as little as possible in the wheels. So the wheels are doing this, okay, circular thing. And the circular thing means there's energy, mass moving this way, and there's mass moving this way, and there's mass moving this way, and there's mass moving that way. And all of those momentums cancel. Okay, and I don't mean they undo each other. I just mean they cancel in the sense that the wheel doesn't go any one of these ways, because not one of them isn't stronger than the other, except the one hitting the ground, obviously. So the one hitting the ground, okay, is in fact, okay, both giving energy to the ground and also losing energy from the cart. It's pulling it from the bearing, and it's pulling it from its own angular momentum. But it's a real thing, okay? So this velocity, if I push this cart, whatever force I push it with will not be converted into a perfect higher velocity because I have to consider these velocities as they have to come out of this. Okay, this velocity, the velocity in this mass moving here, this mv of the wheels, has to be added to the mv of this mass moving in this direction. So you have to add those. You can't pretend that they're independent. They're not independent. To have, like I said, if I push the cart and it just skidded, right? So it skids without the wheels moving. You can understand that this velocity now will have to turn the wheels. So I'll have to lose velocity in this direction to store the velocity in the wheels rolling. So this will slow down for the wheels to speed up. So all of this has to be added up. So it's not, there's no ideal. You know, we can't make an ideal system, but it's certainly not ideal to have a bunch of mass, okay, in the wheels. That's not ideal because you won't be able to measure that momentum. It's invisible. So it won't be visible in the actual motion of the cart. You have to calculate it. All right. So something can be moving, you know, apparently slow, but it has a lot of stored momentum in the wheels. And then the question just becomes, can it deliver that stored momentum into the object? So when the wheels stop, does the bearing hit hard here and then push the cart up? Or does it hit the bottom and push the cart forward? So obviously you can understand the more mass on the cart, the more likely it is you're going to convert the momentum this way. And the lighter the cart, the more likely the angular momentum is going to create motion up rather than forward. So that's another thing to consider, is that it's going to screw up based on how much pressure there is on the bearings, okay, based on how much mass is on top of them. So there's a lot to consider there. And you're pretending it's really simple, and it's not. It's always more complicated than we'd like. All right. Like counting frame rates, it all has to do with, see, I want to move to a strobe system. You know, so there's just no doubt about the timing of motion and getting the accurate velocities. But I really don't want to do these experiments, so whatever. We'll see if I get to it. I mean, it really should be done professionally, but they should be done with a strobe light because camera frame rates are just too unreliable, as I think your video shows, frankly. All right, so I'll just go to the Professor Lewin argument now about, it's an argument I've already made, and I'll make it in this video and hope that you'll pay enough attention to realize that you have some obligation to respond to the accusation that his video is a fake, and it's easily diagrammed as a fake. Alright, so the Professor Lewin experiment. One mass into a two mass, okay, alright, and you end up with extra momentum, okay, 30% more momentum going in this direction. So you start with a momentum arrow that looks like that. You come out of the experiment with a momentum arrow that looks like that. Alright, that's the experiment. Alright, now it's done with these air carts, okay, and they're pretty standard things, okay, pretty easy to just look at and get it, okay, how they're constructed. Now I won't be, look, Stephen patronized me quite a bit, so I will patronize him a little bit and ask him rhetorical type questions. You do understand this is just extruded aluminum, and they just cut it to size. Alright, and they cut carts to size. They'll make a cart that's 10 centimeters, let's say, and they make a cart that's 20 centimeters. This one's going to weigh 1 mass, and this one's going to weigh 2 mass. And that's the way they're cut. So the plain metal is generally sold by every company I know of in basic standard sizes, 1, 2, 3. Okay, and that now the rest is just adding superfluous bits that have to be added to make the carts perform, okay? And the idea would be is you'd never put a weight on one side that you wouldn't put on the other side. You don't want to imbalance the cart, okay, because it won't work well. And Stephen knows that. So looking at one side of the cart, you really know what's on the other side, okay? And so there's not going to be some huge big pile of weight on one side of the cart that isn't going to be represented on the other side. All right, so the carts come with springs, okay, that you can attach. All right, so let's say you wanted to double this standard cart. So let's say this weighs 100 grams, just to make it simple, and this weighs 50. Now you want to double the mass. Well, you got to count the springs. So now you've added 2 springs. Well, you can't just add 2 springs on this cart to double it. You have to add 4. So in the Professor Lewin cart, there's 2 missing springs, okay? 2 missing springs. All right. So there's a weight, okay? A little bar weight right here on both carts. So yeah, this one has 2 weights probably. This one has 2 weights. So it's missing 2 weights, right? Because it needs 4 if I'm going to double the mass. So if this is going to be a 2 mass, if it's going to stay twice as heavy, I have to add twice as many little mass units. Okay, so it's missing 2 metal bars. All right, the flag. Okay, there's a flag to go through the time gate. All right, well, this one has 1 flag. This one has 1 flag. Guess what again? We need another one. It could weigh 10 grams. You know, who knows? Each one of these things could weigh 10 grams. So it's missing a 10 grams worth of flag. Okay, no flag. Then comes the funny part, right? The clay. Now, what they did is they had this strip of flat clay. Okay, it's just like putty, very flat, 1/8 of a millimeter thick. And they put it on the carts, probably just to make the carts a little heavier so they were less wobbly. So if you look at other Professor Lewin videos, you'll see the clay strip. It's a nice flat strip. And presumably, obviously, it'd be on both sides of the cart. Okay. And so what do we see in this example, okay, in this experiment? Well, we see that the clay strip has been crumpled up into a ball, a little golf ball. Now, presumably, there's a clay blob on the other side of the cart. There wouldn't be on one side without there likely being one on the other side. All right, so there's 2 clay balls there. And kind of obviously absent, no clay strip, no clay ball. So it's not missing just 2. It's missing the 2 that are on this cart. But again, remember, you have to double whatever's on here. So it's missing 4. So it's missing 4 golf ball blobs of clay. Alright, so that's a lot of missing. 2 metal bars, 2 springs, a flag, and 4 blobs of clay. That's a lot of weight missing from this cart. And there's nothing else on this cart to in any way account for it. To any way say, oh yeah, but there's something else on here that this one doesn't have. There's nothing on this cart that isn't on this cart. And the real difference is there's stuff on this cart that isn't on this cart. So there's no way this can be twice the mass. It's just not possible. It's not plausible. So, Stephen, do you honestly think this isn't a flaw in his experiment? That this isn't suspect? That this isn't maybe more suspect than the fact that the Mythbusters guys might have measured 49 degrees, okay, from parallel. Instead of 41 from this direction, they measured 49 from this direction. Which one's you think more explainable? Like, this is possible. Is this really possible? Is this a flaw that should just be ignored by everybody? Nobody should want an accounting for this? Nobody should expect it? This isn't, kind of obvious? Alright, so the experiment does something I say is impossible. It creates more momentum in a direction. Okay, and that's what the box is doing. You can't make an experimental box, okay, where you put 100 energies in and you get 130 energies out. You can't do it. That's free energy. So unless the box has uranium in it or something, you can't do it. It has to have a source of energy. There's no source of momentum. There's no source in the experiment. It can't make more momentum come out. Can't happen. That's my argument. Okay, now you don't understand that argument for some reason? Okay, I believe in momentum. Like Descartes, Galileo, and Newton, I think momentum was a perfectly fine answer, and I don't think it ever gets a wrong answer. And I don't think you have any evidence of it ever getting a wrong answer. And you're behaving kind of obnoxiously because I'm just telling you I believe in momentum. And I see absolutely no need for 1/2 mv squared. I don't see where it works or what use it has or anything about it that's worth anything. It just doesn't make any sense at all. It doesn't work in the real world, and there's no evidence of it. And there's no experiments showing it. And even when they crash two cars into each other, they still can't make it happen. And yes, I say xylophone. Okay, xylophones are really those things you bang with sticks. Okay, instead of saying accordion. Okay, sorry. Gee, my mistake. Ugh. The fact is that the cars aren't showing 1/2 mv squared. They're perfectly showing momentum. That's just a coincidence? Like the bowler's not using the 8-pound bowling ball? It's just a coincidence? You know, you really think a bowler can only throw an 8-pound ball 0.4 faster than a 16-pound ball? You really think that's true? Oh, come on. All right, so we'll go through a couple of your experiments and just point out how your results are erratic at best. I don't even know what the right word would be. They're just inconsistent. All right, so how can you argue that this is all stuff I have to believe it? I have to. No, I don't have to. It's not good enough. All right, so let's just go through a couple of the experiments. So the first one I found really offensive is, okay, you call this Gary's cheat. So you take a spring, you compress it the same amount. You put a 1 mass, you put a 2 mass. You push the objects, and all you're going to do is collect them on opposing springs. And the simple argument is this one's going to go twice the velocity. All right, it's going to end up with twice the kinetic energy. So by your 1/2 mv squared, okay, it has twice as much energy as this object. Because it is going to go twice as fast. And there's every indication in your video that it did go twice as fast. And the trick is they both compress the spring exactly the same amount. Because the same force pushed them. They received it as the same force. And it didn't matter whether I had a 10-ton train going 5 miles an hour, or I have a 5-ton train going 10 miles an hour, I have the same energy and I'll get the same result. You called it Gary's cheat. The experiment came out basically as I predicted, and you just pretend it didn't happen. Okay, and so there's no way looking at the video you can say this is going only 0.4 faster. I think that's just a ludicrous proposition, but whatever. All right, so then you did another experiment, okay, and this time you were shooting, what the hell was it? You were shooting balls or something. Well, anyway, you were shooting something through the air. What the hell? I can't remember what it was. It doesn't really matter. Air track. Yeah, that's what it was. It was air track carts. All right, and so you pushed the air track cart, and the problem was you couldn't get the 1 mass, right? So you have a 1 mass and a 2 mass cart. And you couldn't get the 1 mass cart to go twice as fast with the same spring. So you used your Big Pen thing or your solder sucker or whatever, and you couldn't get this to go twice the velocity. It was certainly going more than 0.4 though. So with the same spring compression, it was going faster than 0.4 faster than the 2 mass. But you had to add energy to get it to go actually twice as fast. And then when you got it to go twice as fast, a known velocity of 2 times, right, and you have the other one going 1 velocity, the 2 mass is going 1 velocity, the 1 mass is going 1 velocity, right? The 2 mass is going 1 velocity, the 1 mass is going 2 velocity, sorry. Okay, 1 mass, 2 velocity. All right, so you got them doing the right thing, and then you crashed them into a spring, and again, my prediction is same difference. 10-ton train going 5 miles an hour, 5-ton train going 10 miles an hour, same compression. So what did you get as numbers? Well, my prediction was 12. Your prediction was 16. And what did you get as an answer? 14. And what did you say? Hey, that's the same as 16. It proved it. So obviously you got a number that didn't prove either theory. It's right in between the two answers. How can it be understood as a credible experiment? You're obviously not connected to the physical reality, because you really have to get either this or this if you're going to make an argument here, right? If you're getting something dead in the middle, you know there's something wrong with this process somewhere. Somewhere you've made a mistake. Kind of obvious mistake. All right. And so what was the third experiment? I have to remember what the third one was. Let's see, does it really matter? I don't know if it matters. I'm just saying, can't you see, I mean, that there's no point. You do all these experiments, they come up kind of weird numbers, they're not really that precise. I mean, okay, look, I could do the billiard ball one, you know. You obviously used the lever, you shot it up, you got pretty close. I mean, you got, 11 and 19, right? I mean, it's not 2 to 1, but it's damn close to 2 to 1. So why are you arguing here? It's really far from 10 and 14, okay? 10 and 14 isn't anything like 11 and 19. So come on. You know, why are you arguing that you're proving kinetic energy? These aren't very good proofs of kinetic energy. Sorry. They're pretty good proofs that kinetic energy ain't happening, and that experimentally it's a little hard to account for all the momentum maybe. But frankly, so what? What's the point of arguing when things are this far off? Why should I even argue with these experiments when they're this far off? So if you don't understand why I'm not impressed, I'm sorry. I'm not impressed. Okay? These aren't really consistent results in any way. They're proving all kinds of ambiguous and unaccountable physics. It doesn't make any sense, frankly. Why the errors? Why is it this far off? And you don't have any explanation for why. 1911 versus 14 and 10? That's way off. All right. So, I don't know. Is there anything else? I'll think about it. Well, I thought about it for a second or two, and I said, okay, look, I'm sorry. I can't make, physics is not a 3-minute subject. Sorry. It's just not. Okay. And so, not much I can do about that. You're not interested in paying attention for more than 3 minutes. Okay. But you really haven't countered these arguments. You haven't countered the argument that your results are haywire, that you exaggerate and say this is a proof when it's obviously not a proof. And that you can't. This isn't something I would call credibility. You can't have credibility when you say you've proven something with results this far off. These are not good proofs. I'm sorry. They're just way off of what proof should look like. So as long as you're going to keep calling what you're doing a proof and telling me I have to believe it when your numbers are this far off, I'm sorry. No sale. And some of these experiments I've done, okay, like dropping weights on a scale. Why don't you just drop weights on a scale and see for yourself, okay, that you drop a weight from 4 times the height and it doubles the weight in gravity. It only doubles the weight. It's not 4 times its weight. It's only double. Okay. Twice the velocity, twice the weight, twice the pressure. Not 4 times the pressure, just twice the pressure. All right. Anyway, so what else do I want to say? So thank you for making a video that wasn't garbage in terms of, the personal nonsense. But yeah, that's why I'm sorry. You're telling me emphatically you have a right to mock my intelligence because I don't think you've made a convincing argument. I don't think you've made a convincing argument. I don't think you've responded to any of the accusations I've made about your experiments, about Professor Lewin's experiment. and about the nuances of the physics regarding how we measure things like velocity. It's a more important point here, so I'll think about that for a second. Alright, so look, I've diagrammed a lever and shown how momentum works. It shows you how you can convert one momentum into another momentum. That is, you can change the mass and velocity ratios, and it just converts. By your theory, kinetic energy doesn't convert. It creates energy and loses energy. If I drop the heavy thing on one side and I shoot the light thing on the other side, I make energy. If I do the opposite and drop the light thing, okay, and have the heavy thing, I somehow lose all the energy. It's right back to the physics girl video where she says, okay, I drop the extra weight, I turn a 5-ton train going 10 miles an hour into a 10-ton train going 5 miles an hour, and I lose half the energy. Yet she won't explain how anything got deformed or anything got hot or any of those catastrophes took place. That half the energy disappeared. And I would argue I know, okay, that all I do is put this in a lever. I just drop that 10-ton train going 5 miles an hour on one side of the lever, and I'm going to make a 5-ton train going 10 miles an hour on the other side. The energy isn't been destroyed. There isn't a loss of energy. It didn't get burned up. It didn't fly away. It's still in the 10-ton train, and I can make the 5-ton train with it. And I think you've got to know that. Your own pool ball experiment proves it. The same force produced the 19, okay? The 11 produced the 19. Come on. Alright, so that's probably enough of a video. Yeah. Alright, so I appreciate the better tone, and I will try to... I will try to be... equally balanced in my rhetoric. Yeah, okay. It is a bit of a style change. Anyway, till the next time and such. So this has been at draftphysics.com. Debate physics, and again, debate requires that you respond to what the other person says. Now, you've told me I need to understand Walter Lewin's experiment. I think I do understand every single bit of it. And I think I understand that they just made up the concept of vector and scalar. And there's no such thing as negative momentum. Okay, and just as there's no such thing as negative kinetic energy. And it's all just mush. And you want to believe in it, that's your prerogative, but I don't think you still have any evidence defending it. Any credible evidence. And I don't think you've dealt with the credible evidence that does exist in the world, proving otherwise.